Hi, everybody. It's Professor Mitchell. In this video, we're going to look at volumes using cylindrical shells. Our objectives are to calculate volumes of solids by slicing with cylinders and calculate volumes of solids of revolution using the shell method. As our first example, the region enclosed by the x-axis and the parabola y equals f of x equals 3x minus x squared is revolved about the vertical line x equals -1 to generate a solid, and we want to find the volume of that solid. So on the left-hand side here, you can see a picture of the region as well as the axis of revolution. So when you revolve this region about this line, you get a solid that looks something like what you see here. All right, now in the last section, we talked about the washers method. The washers method would be awkward for doing this problem. And let me try to show you why. So hopefully you remember that when using the washers method, you start by drawing a representative rectangle, which is perpendicular to the axis of revolution. Sorry, that's a little sloppy. And then you have to do an outer radius and an inner radius. Well, because this rectangle is horizontal, the first thing we would have to do is rewrite this equation so that it's solved for x. And because this curve does not pass the horizontal line test, we would actually have to divide this into two curves through this line. So the left half of the parabola would be one function of y, and the right half would be another function of y. It would be pretty complicated. It turns out that it's much simpler to use what's called the shells method, which I'm going to explain to you now. All right. So instead of rotating a horizontal strip of thickness delta y, as I was just describing, we're going to rotate a vertical strip of thickness delta x. This rotation will produce a cylindrical shell of height y sub k above a point x sub k within the base of the vertical strip and of thickness delta x. And I'm going to show you a picture of what this shell looks like in just a moment. We can think of the cylindrical shell shown in the figure as approximating a slice of the solid obtained by cutting straight down through it, parallel to the axis of revolution, all the way around close to the inside hole. We then cut another cylindrical slice around the enlarged hole, then another, and so on, obtaining n cylinders. If we unroll this cylinder and flatten it out, it becomes approximately a rectangular slab with thickness delta x sub k. And again, I'm going to show you a picture of this. All right, so if you're not quite following, it's okay. It'll make sense in a minute. The height of the rectangular slab is approximately y sub k, which is 3x sub k minus x sub k squared. That comes from the equation of the parabola. And its length is the circumference of the shell, which is approximately 2 pi times the radius, or 2 pi times 1 plus x sub k. All right, so here in this kind of gold color, you can see the cylindrical shell of height y sub k, obtained by rotating a vertical strip of thickness delta x sub k about the line x equals -1. The outer radius of the cylinder occurs at x sub k, where the height of the parabola is y sub k, which is 3x sub k minus x sub k squared. All right, and this is a picture I always like to show. So if you take that shell out of the picture, what I'm going to do is imagine cutting it down the side so that I can unroll it. The radius of the shell is 1 plus x sub k, and that's because, if I just go back to this picture, the distance from the y-axis to x sub k is, of course, x sub k, and then the distance from 0 to -1 is 1. So altogether, the distance from here, which is at the center of the shell, all the way out to here is 1 plus x sub k. All right, so that's the radius of the shell. The height of the shell is 3x sub k minus x sub k squared. All right, so now if you cut down the side of the shell and unroll it, you get this approximately rectangular slab. To calculate the volume of a rectangular slab, you just need to do the length times the width times the height. The length is 2 pi times 1 plus x sub k, because that comes from the circumference of the shell. The width, or they're calling it the height, let's go with that. The height of the slab is 3x sub k minus x sub k squared. And then the thickness of the slab is delta x sub k. All right, so what we're doing here is deriving a formula. Hence, the volume of the shell is approximately the volume of the rectangular slab, which is the circumference times the height times the thickness, which comes out to this expression here. All right, summing together the volumes of the individual cylindrical shells over the interval from 0 to 3, because those were the x-intercepts of the parabola, gives the Riemann sum, sum going k equals 1 to n, 2 pi times x sub k plus 1 times 3x sub k minus x sub k squared times delta x sub k. And then if you take the limit as the thickness delta x sub k approaches 0 and n approaches infinity, you get this integral, the integral from 0 to 3 of 2 pi times x plus 1 times 3x minus x squared with respect to x. All right. And then evaluating that integral by first multiplying out these binomials gives you this expression here. Combining like terms and then using the backwards power rule, you find that the volume of this solid is 45 pi over 2. All right, so in general, the volume of the solid generated by revolving the region between the x-axis and the graph of a continuous function y equals f of x, which is greater than or equal to 0, and x between a and b, a also needs to be greater than or equal to L, about a vertical line x equals L, is given by this integral, the integral from a to b of 2 pi times the shell radius times the shell height. Now, oftentimes the shell radius will just be x and the shell height will just be f of x. But for example, in the problem we just did, the shell radius was x plus 1 because we were revolving about the line x equals -1. So moral of the story, it's a very good idea to start by drawing a graph, all right? And then draw that representative rectangle. And from that, you can tell what your shell radius is going to be and what your shell height is going to be. All right, so for the next example, the region bounded by the curve y equals the square root of x, the x-axis, and the line x equals 4 is revolved about the y-axis to generate a solid. And we want to find the volume of that solid. So we will sketch the region and draw a line segment across it parallel to the axis of revolution. At the end of this video, I'm going to talk about how can you decide whether to use discs or washers or whether to use shells. And one of the things that I will repeat when I get to that is that when you're using shells, the representative rectangle is always parallel to the axis of revolution. All right, we're going to label the segment's height, which is the shell height, and the distance from the axis of revolution, which will be our shell radius. All right, so here's the region. It's bounded on top by y equals the square root of x. It's bounded on the bottom by the x-axis, and it's bounded on the right by the line x equals 4. All right, this region is going to be revolved about the y-axis. Okay, so if we're using shell method, we're going to draw that line segment parallel to the axis of revolution. And because it's vertical, that means that this integral will be left in terms of x. So y is a function of x. That is the way we will leave it. The radius of the shell in this problem is just x, because the distance from the y-axis to x is x, right? It's the distance from 0 to x. And the height of the shell is f of x, which is the square root of x. Okay. All right, the integral goes from 0 to 4, and that's because the region goes from 0 to 4. So the volume is again going to be given by the formula integral a to b of 2 pi times the shell radius times the shell height with respect to x, which in this case is the integral from 0 to 4 of 2 pi times x times the square root of x. This integral is simple enough that I think I can just go through it on the slide here. X times the square root of x is x to the 3/2. So we will once again use the backwards power rule to evaluate that integral. The antiderivative for x to the 3/2 is 2/5 x to the 5/2. And I'll let you, if you need to, pause the video and think about when you plug in 4 and plug in 0, this will come out to 128 pi over 5. All right, so to summarize the shell method, we will do one more example at the very end, which I added. Regardless of the position of the axis of revolution, be it horizontal or vertical, the steps for implementing the shell method are as follows. First, draw the region and sketch a line segment across it parallel to the axis of revolution. Label the segment's height or length, which is the shell height, and the distance from the axis of revolution, which is the shell radius. Next, find the limits of integration for the thickness variable. Integrate the product 2 pi times the shell radius times the shell height with respect to the thickness variable, which is either x or y, to find the volume. All right, so here's the slide that I added. A lot of times students will be challenged by trying to decide, should I use the disc or washer method? And by the way, discs are just a special case of washers. That's why I'm saying discs/washers. A disc is just a washer with no hole in it. So should I use the method of the previous section, which is discs or washers, or should I use the method of this section, which is shells? So here's how you can decide. Usually one way is easier than the other. If the functions are in the form y as a function of x, then the representative variable will be vertical because its width is delta x. On the other hand, if they're in the form x as a function of y, the rectangle will be horizontal. If the rectangle is parallel to the axis of revolution, then you need to use shells. And a cute way to remember that is remember that the word shell has a pair of parallel L's in it. Okay, so if the rectangle is parallel to the axis of revolution, use shells. If it's perpendicular to the axis of revolution, then you'll use discs or washers. And sometimes more than one integral is required. So usually what I'll do is try to find the method that won't require more than one integral. I usually also try to do it so that whatever form the functions come in, I can leave them in that form. For example, if they come y as a function of x, I'm going to try to leave it y as a function of x instead of solving that equation for x and rewriting the equations. Okay. All right. So for this example, which I added, we're going to set up the integrals. We're not going to worry about evaluating them. We're just going to set them up, which could be used to find the volume of the solid generated by revolving the region in the first quadrant bounded by y equals 4 minus x squared and y equals 2 minus x about the x-axis using first washers and then shells. All right, so the first thing I'm going to do is make a quick sketch of our region. Okay, so one curve was the parabola y equals 4 minus x squared. So that is an upside down parabola that looks something like this. Y-intercept at 4 and x-intercept at 2. And then the line y equals 2 minus x, which has a y-intercept at 2 and an x-intercept at 2. All right, so the region that we are revolving about the x-axis, let me make a note of that, is this region here. All right. And first we wanted to use washers. So remember washers, with a washer, the rectangle is perpendicular to the axis of revolution. So that means vertical. So if I draw that rectangle, let's say here. Remember for washers, we need an outer radius and an inner radius. The integral is, there we go. It's the integral a to b, oops, pi times the outer radius squared minus the inner radius squared. All right, so in this case, the outer radius is the parabola. So big R of x is going to be 4 minus x squared, and little r of x is going to be 2 minus x. All right, and then we'll use x limits for the limits of integration. So this region starts at x equals 0, stops at x equals 2. So this integral is going to be pi times the integral from 0 to 2 of the big radius, which is 4 minus x squared squared, minus the little radius, which is 2 minus x squared. Okay. Remember, in this example, we're not evaluating these integrals, we're just setting them up. Okay. All right, so now let's talk about how you would use this or use the shell method to do this problem. So I'm just going to redraw the region. Spoiler alert, it's going to be more complicated to do it this way. So if you had your choice, I would say just go with washers. Okay, so there's y equals 4 minus x squared. And here's y equals 2 minus x. Okay. Going about the x-axis. So if we're using shells, the rectangle is parallel to the axis of revolution. So a couple of complicating factors right, with this situation. First of all, the rectangle is horizontal, which means that these functions are going to have to be rewritten as functions of y. So that's one thing. And then another thing, when I go to do the shell height is going to depend on which part of the region I'm in, okay? Because it goes by what curve is on the left and what curve is on the right. All right, so we're going to have to do this as two separate integrals. Okay. All right, but before we get into that, let's rewrite these functions so that they are functions of y. So first, y equals 4 minus x squared. If we solve that for x, first it becomes x squared equals 4 minus y. And then normally I would say be careful here. X could be either the positive or negative square root of 4 minus y. But because we're only looking at the right half of the parabola, it's just going to be the positive square root of 4 minus y. Okay, so that's going to be this curve here. And then y equals 2 minus x. That's a lot simpler. Solved for x, that just becomes x equals 2 minus y. Okay. And that is this curve here. Okay. The interval of integration is going to be from 0 to 4. That's y equals 0 to y equals 4. But it's going to have to be done as two separate integrals. Okay. So let's start with the bottom part. Okay. So first of all, remember the formula. It's integral a to b of 2 pi. I'm going to write it in terms of y, not that it really looks much different. And I'm sorry, my handwriting is a little sloppy. I'm using a different stylus than the one I normally use. And believe it or not, I also put a new case on my iPad. You wouldn't think that the case would have anything to do with being able to write on it, but it does. It makes it awkward for me to figure out where to rest my hand while I'm writing. Anyway, not your problem. All right. Okay, so first, the lower part of the region. That's going to go from 0 to 2. Okay. The radius of the shell is just going to be y. And then the height of the shell, which is this distance here, that's going to be the right curve minus the left curve. Okay. So it's going to look like this: 2 pi times y, which is the radius, times the height, which is the right curve. The right curve was the parabola, so that's the square root of 4 minus y, minus the left curve, which is 2 minus y. Be sure to put that 2 minus y in parentheses. Okay. And that integral is going to give me the volume generated by the bottom part of the region. Okay. To get the rest of it, I have to add the integral from 2 to 4. 2 pi, the shell radius is still going to be y. And this time the shell height is actually going to be a little simpler. The shell height, see, now the straight line has nothing to do with it. It's just determined by the parabola. So the height of that shell is just going to be the square root of 4 minus y. Okay. All right. So again, we're just setting up these integrals. We are not evaluating them. What might be a useful little exercise for you would be to just check and verify, evaluate these integrals. And since this integral here gives the volume of the solid, it should have the same value as the sum of these two integrals. Okay, so check to make sure that those two come out to be the same thing. All right, and that's going to do it for this section, and we will see you next time.